These are the answers to the electron configuration and periodic table practice test. In the video description area, there is a link to the packet that accompanies this video. Now let's begin and take a look at question 1. Question 1 says, the diagrams shown below represent two different electron transitions for the Bohr electron shell model of the atom. Two different colors of light are associated with these electron transitions. Which of the following choices is most likely to represent the colors of light that are associated with each transition? Now, before we analyze the colors of light that are listed in those four choices, A, B, C, and D, I'm going to give you a little background information about this experiment. In your packet that was entitled Electron Configuration, I had presented various forms of electromagnetic radiation, everything from radio waves to X-rays. Now, what you can see at the top of this slide are a few examples of different forms of electromagnetic radiation, or different forms of light. This isn't the entire spectrum, but just a few examples. So on the far left, I see infrared light, and on the far right, I see ultraviolet light. And they are arranged in order of increasing energy, from lower energy on the left to higher energy on the right. Now, between infrared and ultraviolet are the colors of visible light, again, arranged in order of increasing energy from red to orange to yellow to green to blue to violet. So we're going to come back to that diagram when we analyze the four choices that are listed in question 1. Now, in your packet entitled Electron Configuration, I had described the details of an experiment involving hydrogen that produces the bright line emission spectrum for hydrogen. So it says, suppose that a glass tube is filled with hydrogen gas and then electricity is run through the tube. What happens? The hydrogen gas starts to glow with a pinkish color light, and the reason that the gas glows is the following. When the hydrogen atoms receive an input of electrical energy, they absorb energy, and this causes the negatively charged electrons in the atoms to become excited. They jump up to a higher energy level, then these excited electrons will fall back down toward a lower energy level, and when they do this, they release energy in the form of light. So you can see on this slide that there is a gas discharge tube containing hydrogen, and if you pass this light from the glowing hydrogen tube through a prism, the colors of visible light will be separated into 4 different colors, and this is called a bright line emission spectrum. So the 4 colors of the hydrogen's emission spectrum are red, green, blue, and violet, and each one of these colors has a different amount of energy. Also, in your packet entitled Electron Configuration, you had to label a diagram. You had to draw 4 arrows that represent the transitions of electrons traveling from a higher energy level, or an excited state, down toward a lower energy level, toward the ground state. Each electron transition involves a specific amount of energy. So red has less energy for that transition than green, and green has less energy for that transition as compared to blue, and blue has less energy for that transition compared to violet. Now, let's go back and take a look at question 1. So each of these diagrams represents an electron that is traveling from a higher energy level to a lower energy level. But if we examine the details of each transition, we can see that a different amount of energy would be associated with each transition. So on the left, electron transition number 1, that electron is traveling from energy level 5 down to energy level 2. And on the right, electron transition number 2, that electron is traveling from energy level 3 down to energy level 2. So hopefully you can see by comparing the details of each of these diagrams that represent a different electron transition, that the electron transition on the left, involving an electron traveling from level 5 down to level 2, that transition will release more energy than the transition on the right, in which the electron is only traveling from level 3 to level 2. So now that we know that higher energy will be released for the transition on the left, and that lower energy will be released for the transition on the right, we can go ahead and analyze the colors that are listed in these 4 choices, A, B, C, and D. We can compare the relative amounts of energy for each color and then determine which of these 4 choices is correct. So let's start by looking at the 2 colors that are listed for choice A, and they are orange and blue. Now, when we compare the relative amounts of energy for these 2 colors, we can see that orange has lower energy than blue. And that's not consistent with the information in these 2 electron transition diagrams, so we can eliminate choice A. Moving on to choice B, the 2 colors listed are yellow and green. Again, when we compare the relative amounts of energy for these 2 colors, we can see that yellow has lower energy than green. Again, not consistent with the information in these 2 diagrams, so we can eliminate choice B. Now I'm going to move on to choice D, and the 2 colors that are listed are green and violet. When I compare the relative amounts of energy for these 2 colors, I can see that green has lower energy than violet. Again, that's not consistent with the information in the diagrams, so I can eliminate choice D. So why is choice C the correct answer to question 1? It's because the 2 colors of light that are listed in choice C are blue and red, and when we compare the relative amounts of energy for those 2 colors, we can see that blue light has higher energy than red light. And so of the 4 choices listed, choice C is the only choice in which the colors of light that are listed are consistent with the relative amounts of energy associated with each electron transition. So for question 1, choice C is the correct answer. Now let's take a look at question 2. In question 2, it says, the before and after diagrams shown above represent 2 different arrangements for the Bohr electron shell model of the atom. Which of the following statements best describes the change that occurred? So in the diagram on the left, which is the before diagram, we can see that an electron is located in energy level 1. But then that electron has moved to a different energy level. And in the after diagram on the right, now that electron is located in energy level 4. So the electron has moved from a lower energy level, which is the first energy level, to a higher energy level, which is the 4th energy level. And so based on that information in those 2 diagrams, we can go ahead and read the 4 choices, and we can already eliminate choices B and D, because it says that the electron moved from a higher energy level to a lower energy level in choice B, as well as in choice D. Again, it says moved from a higher energy level to a lower energy level, and that's not what's happening. So now we know that the correct answer to question 2 is either A or C. So let's think about whether energy is absorbed or released. In your packet entitled Electron Configuration, I had presented the Bohr electron shell model of the atom, and it says, Bohr suggested that an electron in the ground state could absorb energy as it moves from a lower energy level to a higher energy level. Now, he also said that electrons could release energy when they move from a higher energy level to a lower energy level, but that's not what's happening in the diagrams in question 2. So when an electron moves from a lower energy level to a higher energy level, then it would absorb energy. And so that's why the correct answer to question 2 is choice A. Now let's take a look at question 3. In question 3, it says, the electron energy diagram shown above has been filled in incorrectly. Answer the following questions related to this diagram. Part A. Fix the mistake that was made in the diagram shown above by writing the correct electron energy diagram in the space below. Use the same number of arrows that are shown in the diagram above. Now, before I fix the mistake in this diagram, let me remind you of a rule that I had mentioned in your packet entitled Electron Configuration. So the rule is called the Pauli exclusion principle, and it states that electrons in the same orbital must have opposite spins. And since we use arrows to represent electrons in this diagram, that means that when two arrows are in the same box in this electron energy diagram, they should have opposite spins, so that one arrow is pointing up and the other arrow is pointing down. So that's the mistake that was made in this diagram. So I'm going to put the same number of electrons, but I'm going to put them in correctly into this diagram. So two arrows, one up, one down in the 1s orbital, two arrows, one up, one down in the 2s orbital, and then I'll fill in the remaining 5 electrons into that 2p sublevel like that. So that is now the correct answer for part A. Now, how many arrows are in this diagram? Well, if we count, we have a total of 9 electrons, and this helps us to identify the element that is represented by this electron energy diagram. So 9 electrons, that would mean an atom of fluorine, which is atomic number 9, has 9 electrons, so that is the identity of the element. The symbol is capital F, so now that's the correct answer to part B. So if I just use this electron diagram, I can see 2 electrons in the 1s, so that would be 1s2, 2 electrons in the 2s, that would be 2s2, and in the 2p sublevel, I can see a total of 5 electrons, so 2p5. Now, what I've written is the electron configuration using the electron energy diagram. Now, what I'd like to do is show you how you can determine the electron configuration for an element simply by looking at the periodic table and finding that particular element. When you were first learning how to write electron configurations, I gave you this periodic table, which is labeled with different energy levels, and each letter S, P, D, and F refers to different types of orbitals. This is another way of representing the different energy levels and orbitals on the periodic table. So once you have memorized this particular pattern on the periodic table, once you know where the energy levels are located, and you know the letters S, P, D, and F, and how it follows this particular arrangement and pattern, then you can take your periodic table, you can find a particular element, and starting with 1s2, you can write the electron configuration. So let me show you how that works. So it would be 1s2, that takes care of the 2 elements in the first row of the periodic table, and then 2s2, that gets you as far as the 4th element on the periodic table, which is beryllium, or Be. And now the next part of that electron configuration has to stop at the element fluorine. So it's going to be 2p, but we're not going all the way to the end, so it's not 2p6, it would be 2p5. So that is the electron configuration for the element fluorine, and that's the long form. So the short form uses a noble gas abbreviation. Now we haven't gotten to the noble gas neon, or Ne, for fluorine, so I have to go back to the end of the previous row which would be helium. And if I write the element symbol helium in brackets, then that is an abbreviation for 1s2. The rest of the electron configuration would be 2s2, 2p5. So what you can see for the element fluorine is the long form and the noble gas abbreviated form of the electron configuration. So that is the correct answer to part C of question 3. Now let's take a look at question 4. In question 4, it says the electron energy diagram shown above has been filled in incorrectly. Answer the following questions related to this diagram. Part A. Fix the mistake that was made in the diagram shown above by writing the correct electron energy diagram in the space below. Use the same number of arrows that are shown in the diagram above. Now, before I fix the mistake that was made in the diagram, let me remind you of another rule that is related to writing the correct electron energy diagram. And this was mentioned in your packet entitled Electron Configuration. This is known as Hund's rule. And Hund's rule says that when you have more than one orbital on the same level, for example, with P or D, there's multiple orbitals on the same energy level. As you can see in 2p, there's 3 different boxes that represent 3 different 2p orbitals. So the rule is that each orbital must have 1 electron in it before any orbital can get a second electron. So look at the pattern of how the electrons were added to the 2p sublevel, going from boron to carbon to nitrogen to oxygen. So that first electron in the 2p sublevel for boron is an up arrow, but then for carbon, another box was filled with a different arrow. That means that another electron was added to that vacant or empty orbital. And then for nitrogen, a third electron was added to the 2p sublevel, such that each orbital now has a single electron in it. So moving on from nitrogen to oxygen, now another electron was added to the 2p sublevel, where that first orbital now has 2 electrons in it. So that particular pattern, which is according to Hund's rule, was not followed for this electron energy diagram. And so that's the mistake that was made. Now, the first 2, 4, 6, 8, 10, 12 electrons were done correctly. But we get to the 13th electron, it would go in the 3p sublevel. And then here's the 14th electron, the 15th electron. So now each of those orbitals in the 3p sublevel has a single electron in it, and that final electron would go into that 3p orbital with 2 electrons now. So each of those orbitals had a single electron in it before any of those orbitals got a second electron. So that is the correct electron energy diagram for part A. And there's a total of 16 electrons in this diagram. And if there's 16 electrons, then that would mean we can identify the element by looking on the periodic table. So which element symbol has atomic number 16? That would be sulfur, which is the element symbol capital S. So that is the answer to part B of question 4. Write the symbol for the element represented by the electron energy diagram, and that would be sulfur, which is capital S. In part C of this question, we have to write the electron configuration for the element sulfur. I'm going to show you 2 different ways to do that. First, I'm going to highlight the various sections of this electron energy diagram, starting with 1s2, and then moving on to 2s2, and then moving on to 2p6. The next level would be 3s, so 3s2. And then for the 3p sublevel, there's 4 electrons in the 3p sublevel, so you would finish off this electron configuration with 3p4. Now, here's another way to write that same electron configuration simply by looking at the periodic table. We know where the element sulfur is located, so if we start at the top of the periodic table with 1s2, we can use our knowledge of the pattern of energy levels and the letters S, P, D, and F that represent the different types of orbitals to continue writing the electron configuration for the element sulfur. So in the next row of the periodic table, the second period, it's going to be 2s2, and then finally 2p6. That closes out all of the electrons in level 2. Moving on to the third period of the periodic table, it's going to be 3s2, but now when we get to 3p, we're not going all the way to the end of the row, so it's not 3p6, but rather 3p4, based on where sulfur is located on the periodic table. So that is the long form of the electron configuration for sulfur. So how do we write the abbreviated or noble gas abbreviated form of the electron configuration for sulfur? Well, let's go back to the end of the previous row. So I can see that sulfur is located in the third period, but at the end of period 2, there's the element neon. So neon is the noble gas that is an abbreviation for 1s2, 2s2, 2p6. So all we have to do now is write the rest of the electron configuration, which would be 3s2, 3p4. So what you're looking at is both the long form of the electron configuration for sulfur, as well as the noble gas abbreviated form of that electron configuration. So those are the correct answers to part C of question 4. Now let's take a look at question 5. In question 5, it says the electron energy diagram shown above has been filled in incorrectly. Answer the following questions related to this diagram. Part A. Fix the mistake that was made in the diagram shown above by writing the correct electron energy diagram in the space below. Use the same number of arrows that are shown in the diagram above. Now, before I fix the mistake that was made in this diagram, I will remind you of another rule that you learned when you were studying electron configurations. So again, this is from your packet entitled Electron Configuration. And this rule is known as the Aufbau principle, which states that an electron will occupy the lowest energy orbital that is available. This rule can also be thought of as start at the bottom level and work your way up. So as you can see in this incorrect electron energy diagram, the first boxes that have been completely filled would total 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So the first 20 electrons have been filled in correctly. Now we come to the 3D sublevel. That 3D sublevel should be completely filled before any electrons are added to the 4p sublevel. So that's the mistake that was made, that they put an arrow into the 4p sublevel before completely filling the 3D sublevel. So let me go ahead and count how many electrons do we still have to add to finish off this electron energy diagram. Well, I can see 6 arrows. I'm going to add them one at a time to the 3D sublevel following Hund's rule. So 1, 2, 3, 4, 5. So now each of those 3D orbitals has a single electron in it. And that last electron, which is going to go into the 3D sublevel, would look like that. There's a total of 26 arrows in this diagram. So that is the correct answer for part A. And in part B, they want us to identify the element. So which element on the periodic table would have 26 electrons? That would be an atom of iron, which has the symbol Fe. So the identity of this element would be iron, and again, it has the elemental symbol capital F, lowercase e. So that is the correct answer to part B. In part C of question 5, we have to write the electron configuration for the element iron. I'm going to show you two different ways to do that. The first way is to simply highlight the different parts of this electron energy diagram. So starting at the bottom, that would be 1s2, and then it would be 2s2, and then moving up the energy diagram, it would be 2p6, and then moving up to 3s2, followed by 3p6. The next level would be 4s2, and then I can see 6 arrows in the 3d sublevel, so I will finish off this electron configuration with 3d6. Now, here's another way to write the electron configuration for iron, simply by looking at iron on the periodic table and knowing that you've already memorized those energy levels and those types of orbitals such as s, p, and d. We'll start with 1s2, and then we'll keep going until we get to iron on the periodic table. So after 1s2, it's going to be 2s2, followed by 2p6. So now we're done with the second period, or the second row of the periodic table. And in the third period, it's going to be 3s2, followed by 3p6. After that, we move on to the fourth period. But there's something interesting that happens that you have to remember about that middle section of the fourth period. So the first part would be 4s2, but now it's actually 3d when we're in the middle section of the periodic table from groups 3 to 12. The d is going to be accompanied by an energy level that's actually one level less than the particular row you're in. So even though we're in the fourth row of the periodic table, this section would be 3d. And we're not going all the way to the end of that section. That would be 3d10. We're only going to where iron is, and it's going to be 6. So it's 3d6. So that finishes off the complete electron configuration for the element iron. Now let's take a look at the noble gas abbreviated version. We know where iron is located. If we go back to the previous row and we go all the way to the end, we can see the element argon. So argon is a noble gas, and the symbol argon is an abbreviation for 1s2, 2s2, 2p6, 3s2, 3p6. So all we have to write after the argon in brackets is the rest of the electron configuration, which would be 4s2 and 3d6. So now you're looking at both the long form and the noble gas abbreviated electron configuration for the element iron. So that is the correct answer for part C of question 5. Now let's take a look at question 6. Question 6 says, which of the following electron configurations is incorrect? The way to answer question 6 is to know the pattern of energy levels and the types of orbitals, such as s, p, d, and f, that you've already learned by memorizing that pattern on the periodic table, the pattern of energy levels and types of orbitals. If we look at question 6, we can see that all 4 of these choices begin in the same way. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But the next section of that electron configuration is written as either 3d or 4d. So as I mentioned in question 5, I was talking about the element iron. After 4s2 would be the energy level for 3d. So therefore, looking at the 4 choices in question 6, we can see that choice B is the one that's incorrect, because after 4s2, they wrote 4d10 instead of 3d. So that's the part that's incorrect, which makes choice B the answer to question 6. Now let's take a look at question 7. Question 7 says, which of the following choices indicates the correct electron configuration for the given element? So I will start with choice A, and the elemental symbol is capital C for carbon. Let's go find carbon on the periodic table. So carbon has 6 electrons, and based on the pattern of energy levels and types of orbitals, the electron configuration for carbon should be 1s2, 2s2, and then 2p, but we're not going all the way to the end, so it's not 2p6, it's going to be 2p2. So 1s2, 2s2, 2p2. That's not what we see for choice A. It says 1s2, 2p4. So that's incorrect, so we can eliminate choice A. Moving on to choice B, we have the element sulfur. Now, we've already seen the correct electron configuration for sulfur from an earlier question. That was question 4 from this practice test. So the electron configuration of sulfur, which has 16 electrons, is 1s2, 2s2, 2p6, 3s2, and then for the 3p sublevel, we're not going all the way to the end. It's not going to be 3p6. It's going to be 3p4. So that is the correct electron configuration for sulfur. But we can see, if we look at choice B, they have 3d4 instead of 3p4. That means that that electron configuration is incorrect for sulfur, so we can eliminate choice B. Now, I'm going to move on to choice D, which features the element titanium, has the symbol Ti, and if we find that on the periodic table, titanium has 22 electrons. So again, we'll start with 1s2, 2s2, 2p6, 3s2, 3p6. So now we're in the 4th period of the periodic table. It's going to be 4s2. And then that middle section, the one I've already mentioned before, it's going to be not 4D, but rather 3D. So we're going 3D2, and that will get us to the element titanium on the periodic table. So 4s2 and then 3d2. Now, considering that choice D has 4s2 and 4p2, not 3d2, but rather 4p2, that's incorrect. So we can eliminate choice D, even though we know that the correct answer to question 7 is actually choice C. Let's go ahead and verify that the electron configuration of germanium has 32 electrons, matches what is listed there in question 7. So 1s2, 2s2, 2p6, 3s2, 3p6. So now in the 4th period, it's going to be 4s2, followed by 3d. We're going all the way to the end of that section, so it's going to be 3d10. And then the last part would be 4p, but we're not going all the way to the end of the row. It's going to be 4p2 for the last part for the electron configuration of the element germanium. So what you can see is the correct electron configuration for the element germanium, and that matches what is listed for choice C. So choice C is the correct answer to question 7. Now let's take a look at question 8. Question 8 says, which of the following is the correct way to write the noble gas abbreviated electron configuration for the element krypton, which is atomic number 36? So we can see where krypton is located on the periodic table, but remember that the noble gas abbreviated electron configuration has to give you additional information about where the electrons are located. You cannot simply write the symbol of the noble gas in brackets and nothing else. So we can eliminate choice A. Now let's go ahead and write the complete electron configuration for the element krypton, and then determine the correct way to write the noble gas abbreviated electron configuration. So starting with 1s2, the next part of that electron configuration will be 2s2, followed by 2p6. Now moving from period 2 to period 3 on the periodic table, we have 3s2, followed by 3p6. Now moving to period 4 on the periodic table, it would be 4s2, followed by 3d10, and then finally 4p6. So we cannot use krypton in brackets as the only thing that we write. So let's go to the noble gas that's at the end of period 3. So not krypton, but rather argon. Argon in brackets is an abbreviation for the first 18 electrons of that electron configuration. So AR in brackets is an abbreviation for 1s2, 2s2, 2p6, 3s2, 3p6. So all we have to do now is write the rest of the electron configuration, which would be 4s2, 3d10, 4p6. So what you are seeing here is both the complete and the noble gas abbreviated electron configuration for the element krypton. So the correct answer to question 8 is choice D. Choice B is incorrect because they forgot to include the 3d10 as part of the electron configuration, and choice C is incorrect because they used neon in brackets instead of argon in brackets. So again, the correct answer to question 8 is choice D. Now let's take a look at question 9. Question 9 says, for the element cobalt, which has the symbol CO, how many electrons are located in the 3d subshell? Well, let's go find cobalt on the periodic table. Cobalt has atomic number 27, so it has 27 electrons in that atom. And let's start with the complete electron configuration for the element cobalt. So beginning with 1s2, and then followed by 2s2, 2p6. Moving on to the third period, it would be 3s2, followed by 3p6. And now in the fourth period, it's going to be 4s2. And remember, that middle section of the fourth period is actually 3d. So if we count how far cobalt is in that 3d section, it would be 1, 2, 3, 4, 5, 6, 7. So the last part of the electron configuration for cobalt would be 3d7. So now we know that there are 7 electrons located in the 3d subshell for the element cobalt. So that makes choice B, 7, the correct answer to question 9. Now let's take a look at question 10. Question 10 says, a certain element has the electron configuration shown above. Which of the following is the correct symbol for this element? If we look on the periodic table, remembering the pattern of energy levels and types of orbitals, S, P, D, and F, we can look at the given electron configuration and find the location of that element on the periodic table. So starting with 1s2, and then moving on, 2s2, 2p6, 3s2, 3p6. Beginning the fourth period of the periodic table, it's going to be 4s2, followed by 3d10, and then 4p6. Now moving on to the fifth period of the periodic table, it would be 5s2 followed by 4d10 and then 5p6. Now we're in the sixth period of the periodic table, but as you can see, there's a little bit of a break in the sequence. The lanthanide series continues with elements 58 to 71, and that's actually going to be labeled as 4F. So watch what happens next. When I'm in the sixth period, it's going to be 6s2 followed by 4f14. So I'm going to highlight that section of the periodic table, and then 5d7. So if I count 1, 2, 3, 4, 5, 6, 7, I land on the element IR, which has atomic number 77. So that is the element iridium, has the symbol IR, which means that the correct answer to question 10 is choice D. Now there's a much simpler, a much easier way to identify the element. All you have to do is simply count the number of electrons by counting the total number in the superscripts of this electron configuration. So if I count just the superscripts in this electron configuration, I will get a total of 77. So 10 electrons for the 1s2, 2s2, 2p6, plus 8 more electrons, so 10 plus 8 is 18. 18 plus 18 is 36. 36 plus 18 is 54. 54 plus 2 is 56. 56 plus 14 is 70. And then 70 plus 7 is 77. And since 77 is the atomic number of the element, now we know that the symbol of the element that is represented by this electron configuration is IR. So the correct answer for question 10 is choice D.
Now let's take a look at question 11. In part A, it says to circle the electron configurations that represent two different elements that are located in the same period on the periodic table. We are given 6 different electron configurations, but we can use the technique that I showed you at the end of question 10 by simply counting up the total number of electrons, involving that process of adding up the superscripts in the electron configuration. This will give us not only the total number of electrons, but also how to find that element on the periodic table. It will be the atomic number of that particular element. So starting with the first electron configuration, it's 1s2, 2s1. That's a total of 3 electrons. On the periodic table, that would be the element lithium, or Li. In our next electron configuration, 1s2, 2s2, 2p6, 3s2, 3p3, that's a total of 15 electrons, and that would represent the element phosphorus, which has the symbol P. Moving on to the next electron configuration, if we add up the total number of electrons, it turns out to be a total of 31, and that would represent the element gallium, which has the symbol Ga. Our next electron configuration has a total of 23 electrons, and that would represent the element vanadium, which has the symbol V. Our next electron configuration, if we add up the total number of electrons by adding up the superscripts, that gives us a value of 37, and that would be represented by the element rubidium, which has the symbol Rb. And then finally, the last electron configuration in part A only has 2 electrons, and that would represent the element helium, or He. Now, we're looking for 2 elements that are located in the same period. A period is a horizontal row on the periodic table. So I've highlighted that vanadium and gallium would be the correct electron configurations that should be circled in Part A. In your packet that was entitled Periodic Table, you learned that a period is a horizontal row on the periodic table and that there are 7 periods, and you can see they are numbered from 1 through 7. So vanadium and gallium are located in period 4. So the answer to Part B would be the symbol of those two elements, so vanadium and gallium, V and Ga, and they are located in period 4. So that's the correct answer to Part C. So now you can see the correct answers to all parts of question 11. Now let's take a look at question 12. Question 12 is similar to question 11. In Part A, it says circle the electron configurations that represent 2 different elements that are located in the same group on the periodic table. So now we're looking for 2 elements that are located in the same group, which is a vertical column on the periodic table. We'll use the same technique that we used in question 11, Part A. We'll count up the total number of electrons for each of these 6 electron configurations, and that total number of electrons also will represent the atomic number of that element. So starting with our first electron configuration, the total number of electrons is 15. So that would correspond to the element phosphorus. Our next electron configuration has a total of 8 electrons, and that would correspond to the element oxygen. So I will highlight each of these 6 elements, and then we'll see which 2 elements are located in the same group or vertical column on the periodic table. Our next electron configuration has a total of 31 electrons, and that would correspond to the element gallium, or Ga. In our next electron configuration, there is a total of 35 electrons if we add up the superscripts. So 35, that is the atomic number of the element bromine, which has the symbol Br. In our next electron configuration, there are 10 electrons, and that would be represented by the element neon, which has the symbol Ne. Now, so far, we haven't found 2 different elements that are located in the same group or vertical column. So in our last electron configuration in Part A, if we add up the total number of electrons, we get a value of 34. So 34 corresponds to the atomic number of the element selenium, which has the symbol Se. And now we can see that oxygen and selenium are located in the same group on the periodic table. In your packet entitled Periodic Table, you learned that there are 18 groups on the periodic table, and they're numbered from 1 to 18. So oxygen and selenium are located in group 16. So that will give you the answer to parts B and C of question 12. The symbols of the elements are O and Se. We circled the 2 electron configurations that are representing 2 elements in the same group. And again, oxygen and selenium are located in group 16. So these are the correct answers to question 12. Now let's take a look at question 13. Question 13 says a certain element has the electron configuration shown above. How many valence electrons does this element have? Now in your packet that is entitled Valence Electrons and the Charges on Ions, you learned how to count the number of valence electrons by looking at the electron configuration. So on this slide you can see question 13 of that particular packet says that the elements located in group 17 are called the halogens. And 3 different elements that are located in group 17 are fluorine, chlorine, and bromine. You can see the electron configuration of each element, and I've drawn a circle around the valence electrons, which are the electrons that are located in the highest energy level of that element. So for fluorine, I circled 2s2 and 2p5. And for chlorine, I circled 3s2 and 3p5. Now for bromine, I only drew a circle around 4s2 and 4p5. I did not include the 3d10 electrons because we're only considering the electrons in the highest energy level for that element. And since level 4 is higher than level 3, I did not include those 10 electrons. So each of these elements, fluorine, chlorine, and bromine, has a total of 7 valence electrons. Now, let's go back and take a look at question 13 of this practice test. I can draw a circle or highlight 4s2 and 4p5. Again, this is the element bromine, and so that makes choice B, 7, the correct answer. But here is another way that you could have determined the answer to this question. We've seen that if you add up the superscripts in the electron configuration, that total number of electrons allows you to find the element on the periodic table. So the total number of electrons in this electron configuration that we were given is equal to 35. So 35 represents the element bromine, or Br. And then in your packet entitled Valence Electrons and the Charges on Ions, you learned this pattern for valence electrons, that as I move from left to right across the periodic table, we have 1, 2, I'm skipping that middle section of the periodic table, and then we have 3, that would be group 13, and then 4, 5, 6, 7, 8. So now you can see that since bromine is located in group 17, it would have 7 valence electrons. So another way to determine that the correct answer to question 13 is choice B, 7. Now let's take a look at question 14. In question 14, it says magnesium, Mg, will change its number of electrons when it forms a stable ion. Which of the following represents the correct electron configuration of the stable magnesium ion? So the first thing that we have to do is determine what happens to magnesium when it forms a stable ion. In your packet that was entitled Valence Electrons and the Charges on Ions, you learned this particular pattern for different elements on the periodic table. That the elements in group 1, the alkali metals, when they form an ion, they normally lose 1 electron to have a charge of +1. And the elements in group 2, the alkaline earth metals, they normally lose 2 electrons to form a stable ion, and they would have a charge of +2. For the elements in group 13, if they form a stable ion, they would lose 3 electrons to give an ion with a charge of +3. And then I skipped over to group 15. So in the elements of group 15, those elements will gain 3 electrons to form a stable ion with a charge of -3. The elements in group 16, those atoms would normally gain 2 electrons to form a stable ion with a charge of -2. And then in group 17, the halogens, they would normally gain 1 electron to form a stable ion with a charge of -1. So let's go determine where magnesium is located on the periodic table so we can figure out what the charge on that ion would be. So this is also a summary of that pattern of the charges on the ions. And we can see that magnesium, which is located in group 2 on the periodic table, would normally form an ion with a charge of +2. So magnesium loses 2 electrons to become an ion with a charge of +2. Now let's write the electron configuration for the element magnesium. It's going to be 1s2, 2s2, 2p6, 3s2. So that is the electron configuration of the atom magnesium, not the ion, but the atom. So the correct answer to question 14 is not choice B, since we know, based on where magnesium is found and that pattern of charges on ions, that magnesium loses 2 electrons to become a stable ion, we're going to remove the 3s2 portion of that electron configuration since it loses 2 electrons. So the correct answer to question 14 is choice A, 1s2, 2s2, 2p6. That is a total of 10 electrons because magnesium, which has 12 electrons, lost 2 electrons to form a stable ion with a charge of +2. So the correct answer to question 14 is choice A. Now let's take a look at question 15. In question 15, we are given electron energy diagrams, and the instructions are to fill in each diagram with the correct number of arrows. Each arrow represents 1 electron. So I'm going to start with the electron energy diagram for a nitrogen atom. So on the periodic table, I can see that nitrogen has atomic number 7, so there should be 7 electrons in this electron energy diagram. I'll start with 1s2, so 1, 2, and then moving on to 2s2, 3, 4 electrons, and then for the 2p sublevel, I'm going to follow Hund's rule, so 5, 6, 7 electrons. So that is the answer for that particular diagram. Now the other diagram that I have to fill involves an ion. Just to remind you that nitrogen is located in group 15 on the periodic table. So the elements in group 15, they normally gain 3 electrons to form a stable ion with a charge of -3. So there's nitrogen in group 15. Nitrogen would normally gain 3 electrons to become a stable ion with a charge of -3. So if I'm gaining 3 electrons, that means that my total number of electrons changes from 7 to 10. So all I'm going to do is take 3 more electrons and add them to the 2p sublevel. So that would be 8, 9, 10. So now I have a total of 10 electrons for the nitrogen ion, which has a charge of -3. In our next diagram, we have a calcium atom, and then we have a calcium ion. So for the calcium atom, calcium has atomic number 20, so there should be a total of 20 electrons. When I add electrons to this diagram, so 2 electrons in the 1s, and then 3, 4, 5, 6, 7, 8, 9, 10. That's a total of 10 electrons. I'm up to level 2. 11, 12, 13, 14, 15, 16, 17, 18. Now I get to that last box in that diagram, 19, 20. So all of these boxes were filled, and that's a total of 20 electrons. Moving on to calcium, the ion. Calcium is a member of group 2, the alkaline earth metals, and calcium will lose 2 electrons to form a stable ion with a charge of +2. So I already have 20 electrons in that diagram on the left. I'm going to simply take away 2 electrons. So now my total is 18. So these are the correct answers to question 15, filling in the diagram with the correct number of electrons. Now let's take a look at question 16. In question 16, we are given a table, and in this table there are 7 different rows, but each row has only been filled with a partial amount of information. So the instructions in question 16 is to fill in the table with all of the missing information. So I'm going to start with the first row in which I am given an electron configuration. So what I can do is simply add up the superscripts and then go find the element that has that particular atomic number for the total number of electrons. So if I add up the superscripts in this electron configuration, I get a total of 56 electrons. And on the periodic table, the element that has atomic number 56 is barium, and it has the symbol Ba. Now, for the other columns of this table, it asks, how many valence electrons does this atom have? And when this atom forms a stable ion, what charge does it have? I'll start with those questions. So this is the pattern that you have learned in terms of valence electrons and the charge when that atom forms a stable ion. So barium, or Ba, it is located in group 2. It has 2 valence electrons, and when it forms a stable ion, it will have a charge of +2. So 2 valence electrons and a charge of +2 on the stable ion. Now that last column says when this atom forms a stable ion, it has the same number of electrons as which noble gas? So barium, the atom, has 56 electrons. But when barium, the atom, loses 2 electrons to become a barium ion with a charge of +2, that total changes from 56 to 54. And 54 is the same number of electrons as the noble gas xenon, which has the elemental symbol Xe. So now that row is complete. Moving on to the next row of the table, I will start by adding up the total number of electrons from the electron configuration, and that total number of electrons is 13. So on the periodic table, the element that has atomic number 13, that is aluminum, which has the symbol Al. In terms of valence electrons and the charge on the stable ion, this is the pattern for valence electrons and the charge on the ion. Aluminum is located in group 13. It has 3 valence electrons, and it normally forms an ion with a charge of +3. So 3 valence electrons, and the charge on the ion is +3. Now for the noble gas, aluminum loses 3 electrons to become an ion with a charge of +3. That means that the total number of electrons changes from 13 to 10. And so 10 is the number of electrons for the noble gas neon, which has the elemental symbol Ne. Now, in the next row of this table, we are not given the electron configuration of the atom, but we are given the elemental symbol. So for As, which is the element arsenic, it has a total of 33 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So now I'm in the 4th period of the periodic table. 4s2 is followed by 3d10, and then finally 4p3 would get me to the element arsenic. So that is the complete electron configuration. If you'd like to write the noble gas abbreviated electron configuration for this element, you can go back to the end of the previous row. So arsenic is located in period 4, but at the end of period 3 would be the element argon. If I put Ar in brackets, that abbreviates the electron configuration up through 3p6. And then I would simply write after Ar in brackets 4s2, 3d10, and 4p3. So you're looking at both the complete and the noble gas abbreviated electron configuration for this element. So in the table, you could either write the complete electron configuration or the noble gas abbreviated version if you prefer to do that. So either this answer or this answer is correct. Now, moving on to the valence electrons and the charge on the stable ion. Here is that pattern for valence electrons and the charge on the ion. So arsenic is located in group 15 on the periodic table. It has 5 valence electrons, and it would normally form an ion with a charge of -3. So 5 valence electrons and a charge of -3. When arsenic forms a stable ion, it gains 3 electrons to have a charge of -3, that means that the total number of electrons will change from 33 to 36. And 36 represents the same number of electrons as the noble gas krypton, which has the symbol Kr. In the next row of this table, let's write the electron configuration for the element chlorine. So chlorine has 17 electrons, and its electron configuration is 1s2, 2s2, 2p6, 3s2, and then finally 3p5, where we stop at 17 electrons. So 1s2, 2s2, 2p6, 3s2, 3p5. How can we abbreviate that with a noble gas? Well, since chlorine is located in period 3, we can go to the noble gas at the end of period 2, which is neon. So neon abbreviates the electron configuration up through 2p6, and then after writing neon in brackets, the last part of that electron configuration would be 3s2, 3p5. So you're looking at both the complete electron configuration for chlorine and the noble gas abbreviated version. So you could either write this or you could write this. Either one of these electron configurations is correct. And now let's move on to the valence electrons and the charge on the stable ion for chlorine. So where chlorine is located on the periodic table, it is a halogen. It's located in group 17. It has 7 valence electrons, and it normally forms an ion with a charge of -1. So 7 valence electrons, and the charge on the ion is -1. When chlorine forms a stable ion with a charge of -1, it gains 1 electron. So that changes the total from 17 to 18, and 18 is the number of electrons for the noble gas argon, which has the symbol Ar. Now for sodium, Na, its electron configuration is written as 1s2, 2s2, 2p6, and then finally 3s1. The noble gas abbreviated electron configuration would take advantage of the fact that neon is in the end of period 2, and that takes care of the 1s2, 2s2, 2p6. So just simply writing neon in brackets takes care of 10 electrons, and then all you'd have to do is write 3s1 after that. So you're looking at the complete and the noble gas abbreviated electron configuration for the element sodium. So you could either write this or you could write that. Either one of these would be the correct electron configuration for the element sodium. Now, for the number of valence electrons, sodium is located in group 1. It has 1 valence electron, and it normally forms a charge of +1 when it forms a stable ion. So 1 valence electron and a charge of +1. When sodium loses 1 electron to become a stable ion with a charge of +1, the total number of electrons changes from 11 to 10. So as an ion, it would have 10 electrons, which is the same as the element neon. In the next row of this table, we are not given the element symbol, and we're not given the electron configuration of the atom. But what we do know about this element is it has 2 valence electrons. When it forms a stable ion, it has a charge of +2, and it has the same number of electrons as the noble gas krypton when it forms a stable ion. So based on the number of valence electrons, we know that this element is located in group 2. So 2 valence electrons, it has a charge of +2. So the element is located in group 2 on the periodic table. When this element forms a +2 ion, it loses 2 electrons. So therefore, this positive 2 ion has the same number of electrons as krypton. That means it has 38 electrons as an atom. Because if you take away 2 electrons from 38, it brings you to a total of 36, and that is the same number of electrons as the noble gas krypton. So now we know that the element symbol is for strontium, that would be Sr. Now let's write the electron configuration for the element strontium. So for strontium, that electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, followed by 3d10, 4p6, and then the last part would be 5s2. So what you're looking at is the complete electron configuration for the element strontium, or Sr. Now, for the noble gas abbreviated version, we can go back to the end of the previous row. So strontium is in period 5, and at the end of period 4 would be the noble gas krypton. That takes care of 36 electrons, and all we have to do is write 5s2 after that. So you're looking at both the complete and the noble gas abbreviated electron configuration for the element strontium. So you could either write all of this as your electron configuration, or you could write Kr in brackets followed by 5s2. So either this or this would be the correct electron configuration. And now moving on to the last row of this table. Again, we don't know the element symbol, we don't know the electron configuration of the atom, but we know it has 6 valence electrons, and it normally forms an ion with a charge of -2, and then that stable ion would have the same number of electrons as the noble gas argon. So 6 valence electrons, that means that the element is located in group 16 of the periodic table. So this element is located in group 16 on the periodic table. When this element forms a stable ion with a charge of -2, it gains 2 electrons and has the same number of electrons as argon. So that means that the identity of the element is sulfur, which has atomic number 16. Because if you gain 2 electrons, your total number of electrons would change from 16 to 18, and 18 is the same number of electrons as argon. So now we know that the element symbol for sulfur is capital S. Let's write the electron configuration for sulfur. And the electron configuration for sulfur would be 1s2, 2s2, 2p6, 3s2, and then finally 3p4. So that's the complete electron configuration. Sulfur is located in period 3. At the end of period 2 is the noble gas neon. So neon would be the abbreviation for 1s2, 2s2, 2p6, and then after writing neon in brackets, you could write the rest of the electron configuration, which is 3s2, 3p4. So you're looking at both the complete and the noble gas abbreviated electron configuration for the element sulfur. So you could either write this, or you could write that. Either one of these electron configurations would be correct. Now let's take a look at question 17. In question 17, it says, fill in the following table with all of the missing information. So in your packet that was entitled Valence Electrons and the Charges on Ions, you learned the names of 4 different families on the periodic table. We have alkali metals in group 1, alkaline earth metals in group 2, halogens in group 17, and noble gases in group 18. Alkali metals in group 1, alkaline earth metals in group 2, halogens in group 17, and noble gases in group 18. So let's go ahead and fill in those four family names. Alkali metals in group 1. Alkaline earth metals is already filled in for you in this table. Halogens in group 17, and noble gases in group 18. All we have to do now to complete this table is fill in the correct number of valence electrons and then the charge on the ion when it forms a stable ion. So here is that pattern. So alkali metals in group 1, they have one valence electron, and they normally form an ion with a charge of +1. Alkaline earth metals in group 2, they have two valence electrons, and they normally form an ion with a charge of +2. Now in group 15, there's no special family name to know, but here are the elements in group 15. They would have 5 valence electrons, and when they form a stable ion, the charge would be -3. For the halogens in group 17, they have 7 valence electrons, and they normally form an ion with a charge of -1. And the noble gases have 8 valence electrons, and the charge on the ion is 0 because they don't normally form ions or compounds at all. So there are the correct answers to question 17. Now let's take a look at question 18, which says, which of the following correctly identifies the horizontal trend in atomic radius and provides the correct explanation for this trend? So in your packet that is entitled Periodic Table, you learned that as you move from left to right across a period, the atomic radius values decrease. And as far as the explanation for this horizontal trend, it is the following: that as you move from left to right across a period, the number of protons in the nucleus increases. And when there are more protons in the nucleus, this causes the valence electrons to be more strongly attracted toward the nucleus and pulled in more tightly. And this explains why the values for atomic radius decrease as you move from left to right across a period. So now, looking at the four choices in question 18, we can eliminate choices C and D because we know that as you move from left to right across a period, the atomic radius decreases. But the explanation is listed in choice A. The number of protons increases, which causes the valence electrons to be more strongly attracted toward the nucleus. So the answer to question 18 is choice A. Now let's take a look at question 19, which says, which of the following correctly identifies the vertical trend in atomic radius and provides the correct explanation for this trend? So in your packet entitled Periodic Table, you learned that as you move from top to bottom down a group, the atomic radius values increase. And the explanation for this trend is the following: that as you move from top to bottom down a group, the number of occupied energy levels in the atom increases. And if an atom has a greater number of occupied energy levels, then its valence electrons will be located at a farther distance from the nucleus. And this explains why the values for atomic radius increase as you move from top to bottom down a group. So looking at the choices for question 19, we can eliminate choices A and B because we know that as you move from top to bottom down a group, the atomic radius increases. And the correct explanation is listed in choice C. The number of occupied energy levels increases, and the valence electrons are located at a farther distance from the nucleus. So the correct answer to question 19 is choice C. So as you can see in this diagram, here is a summary of the atomic radius trend. That as you move from left to right across a period, the atomic radius values decrease, and as you move from top to bottom down a group, the atomic radius values increase.
Now let's take a look at question 20. In question 20, it says, answer the following questions about the elements magnesium, chlorine, and strontium. In part A, we have to fill in the missing information in the following table. Let's start with the electron configuration for each of these three elements. So for magnesium, its electron configuration would be 1s2, 2s2, 2p6, and then finally 3s2. That is the complete electron configuration. Since magnesium is located in period 3, you could use the noble gas at the end of the previous row. So at the end of period 2, that would be neon. And if you write neon in brackets, that abbreviates 1s2, 2s2, 2p6, and then all you would have to write after neon in brackets would be 3s2. So there is both the complete and the noble gas abbreviated electron configuration for the element magnesium. Our next element is chlorine. So chlorine has 17 electrons, and its electron configuration would be 1s2, 2s2, 2p6, 3s2, and then finally 3p5. That would be the complete electron configuration for the element chlorine. And since the noble gas abbreviation would also include neon, which is at the end of period 2, then after you write neon in brackets, the rest of that electron configuration for chlorine would be 3s2, 3p5. So there is both the complete and the noble gas abbreviated electron configuration for the element chlorine. Now for strontium, it has a total of 38 electrons. So let's write the complete electron configuration for strontium, and then we can see how that can be abbreviated with a noble gas. So for strontium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and now in period 4, that would be 4s2, followed by 3d10, and then 4p6. And then the last part of strontium's electron configuration would be 5s2. So that is the complete electron configuration for strontium. Now strontium is in period 5, but the noble gas at the end of period 4 is krypton. And that would abbreviate all but 2 of the electrons in strontium's electron configuration. So if I write krypton in brackets, that's Kr in brackets, all I have to write is 5s2 to complete that electron configuration. So there is the complete and the noble gas abbreviated electron configuration for the element strontium. So again, your answer to number 20, part A, could look like this, the complete electron configuration, or you could choose to write the noble gas abbreviated version, and that would also be correct. Our next question to answer in this table is metal or nonmetal. In your packet entitled Periodic Table, you learned that there are 3 types of elements: metals, nonmetals, and metalloids. And we can see where magnesium and strontium and chlorine are located. Magnesium and strontium are classified as metals. Chlorine is classified as a nonmetal. So magnesium is a metal, chlorine is a nonmetal, strontium is a metal. Now with respect to the family name, since magnesium and strontium are located in group 2, they are classified as alkaline earth metals. And since chlorine is located in group 17, it's classified as a halogen. So magnesium is an alkaline earth metal, chlorine is a halogen, and strontium is also an alkaline earth metal. With respect to the number of valence electrons, magnesium and strontium are in group 2, so they have 2 valence electrons. Chlorine is in group 17, it has 7 valence electrons. So 2, 7, and 2. And for the charge on the ion, when it forms a stable ion, magnesium and strontium would form an ion with a charge of +2. Chlorine would form an ion with a charge of -1. So +2, -1, and +2. Now, in part B of this question, we have to arrange these three elements in order of increasing atomic radius from smallest to largest. So here is that diagram that I showed you earlier for the atomic radius trend. Atomic radius increases as you move from top to bottom down a group. So strontium would be in the same family as magnesium, and strontium would have a larger atomic radius than magnesium. An atomic radius decreases as you move from left to right across a period. Chlorine is in the same period as magnesium, so chlorine would be smaller than magnesium, and strontium would be larger than magnesium, based on these periodic trends in atomic radius. So of the three elements in this group that we're considering, strontium has the largest atomic radius of these three, and chlorine has the smallest atomic radius of this set of three. So to answer part B of question 20, chlorine has the smallest atomic radius, and strontium has the largest atomic radius. Now, the final question in question 20, so part C, says to arrange these three elements in order of increasing ionization energy values from smallest value to greatest value. So in your packet entitled Periodic Table, you learned about the periodic trend in ionization energy. The ionization energy of an element is a property that refers to the energy required to remove the outermost electron away from the atom. It's an approximate measure of how strongly that electron is attracted toward the nucleus. And so, based on the ionization energy values that are listed in the table, there are two periodic trends that we can see, that as you move from left to right across a period, the general trend is that the ionization energy values increase, and that as you move from top to bottom down a group, the general trend is that the ionization energy values decrease. And so in your packet entitled Periodic Table, you learned about the explanation for both the horizontal and vertical trends in ionization energy. So they're opposite to the trend in atomic radius. So as you move from left to right across a period, the atomic radius values decrease. In general, the smaller the atomic radius is, the higher the ionization energy value will be. So a smaller atom has valence electrons that are located closer to the nucleus and held more tightly. Therefore, it should require more energy to remove the valence electron from a smaller atom. And then with respect to the vertical trend, again, it's also opposite to the trend in atomic radius. So as you move from top to bottom down a group, the general trend is that the ionization energy values decrease, whereas the atomic radius values increase. So the larger an atomic radius is, the lower the ionization energy value will be. A larger atom has valence electrons that are located farther away from the nucleus and held more loosely. Therefore, it should require less energy to remove the valence electron from a larger atom. So now let's go back and take a look at these three elements, chlorine, magnesium, and strontium. So we already know the trend in atomic radius. Chlorine is the smallest in this set of three, and strontium is the largest in this set of three. So how does the atomic radius help us to understand what's going on in terms of the ionization energy value? Well, again, it's kind of an opposite trend. Strontium has the largest atomic radius. Its outermost electron is farther away from the nucleus and easier to remove, so strontium would have the smallest ionization energy value in this set of three. And on the other end, since chlorine has the smallest atomic radius in this set of three, its outermost electron is closer to the nucleus and more difficult to remove, so chlorine would have the largest ionization energy value in this set of three. So strontium, smallest ionization energy value, and then chlorine, greatest ionization energy value. All right, well, that is the correct answer to parts B and C of question 20. And question 20 is the last question in this practice test. So I hope that you found all of these answers and explanations helpful. Thanks for watching, and good luck studying for your test on electron configuration and periodic table.